Yeah, I'll blame it on George. No, so part of the reason is because we spent about 4 hours on this algo mini course, and if anyone, you've already overloaded on that. Ryan, my former PhD student, postdoc, is going to give another talk on algo trading tomorrow afternoon. So there's enough exposure to that topic. I wanted to talk about something else. If you're interested in seeing the 10-minute or 5-minute version of it, let me know. I'll sit down with you and go through the slides. Okay, so we'll be happy to do that. And just in case those of you who were not here and missed the mini course that I delivered on the weekend, we actually have a book on algorithmic and high-frequency trading that's been published by Cambridge University Press, out since August. It's a nice collection of ranging from the financial economics, data, off into stochastic control, and how that's applied in algorithmic trading, and I suggest you check it out. Okay, so on with this topic, which is model uncertainty in commodities. So I'm glad that Chris mentioned something about parameter uncertainty and not knowing what the actual model is that you're using, or not the model, but in that case, parameters. Here I'm going to look at how uncertainty in the model itself is something that is going to affect the way that you should trade. Okay? And this is work done together with my collaborator Alvaro and current PhD student Jen. And let's move on to the idea. So as Chris mentioned, if you just look at some historical data and you estimate a model, obviously you know that that model is probably, the parameters are certainly not going to be pinpoint and having a confidence interval that's extremely tight. There's going to be some range if you assumed a parametric model. Not only that, you're not even entirely sure that the model itself is the correct model for the data. You've made an assumption. Okay? So and this is certainly true in commodities, this is true in many other areas, but we're going to focus in on the commodity context here. And we want to look at eventually how model uncertainty or model ambiguity, as it's sometimes called, affects prices of derivatives. We'll start off with just forward contracts, and then we'll talk about some other derivative contracts here. So let me start this out by asking for a show of hands. Who knows about the Ellsberg paradox? Okay, so I see about 10 people in the audience. So that's a reasonable amount of you. But for those who don't, I'm going to give you a little experiment. Imagine you have this. You have a box, and there's a total of 100 marbles in this box. 40 of them, you're told, are red, and the remaining 60, you're told, are black or green, or black and green. I haven't told you how many black, how many green. The total of that, though, is 60. That's the box. I take it, shake it up, pull out a marble at random. I don't show it to you yet, and I ask you, I'm going to give you the choice of 2 games to play. You either play game A, where once I reveal the marble, if it's red, you get $100. Or you get to play game B. Once I reveal the marble, if it is black, you get $100. How many of you would prefer to play game A? And so let's start with game A. Yeah, I've told you 60. I told you there's 60 in total that are black and green, but nothing more. I've told you nothing more. Yeah, nothing more. That's the only information you have. How many prefer game A to B? Let's see by a show of hands. I would say that's definitely a majority of the audience, because you have to trust me. That's a majority of the audience. So we've got most people choosing game A. Now I'm going to say, forget about game A and B. Same box. I haven't changed anything. I haven't revealed the marble yet. I'm going to give you a choice now between 2 alternate games. Game C, which says you get 100 if the marble is red or it's green once I reveal it. Or game D, where you'll get 100 if it's black or it's green. Okay, so think about it for a second. How many of you prefer game C? Okay, a handful. How many prefer game D? I prefer game C. How many prefer game D? Okay, again, a majority for game D. Okay, so so here's the thing. If you chose game A to B and you were a rational maximal expected utility, if you were maximizing expected utility of your wealth, you should rationally choose game C as well. If you chose A over B, you should have chosen, you should have chosen C over D. Easy way to see this. If you choose A over B, you've sort of subtly assumed that the probability of a black marble is smaller than 40%. That's kind of what you did. And if you just work backwards as to what you assume subtly when you choose game D to C, is that you've actually assumed the probability of a black marble is greater than 40%. you've made an inconsistent assumption. But why did you make that assumption? This is the important thing, is why did you make that decision? It's not that, economic theory is not there to tell you that agents are constantly computing things, right? They're saying they make decisions, and then we try to explain with a model, with a mathematical framework, why they make decisions of that type. So in this case, you made the decision to choose D over C because in model D, you knew the probability of winning was 60%. You were sure of it. The probability of winning here, you know, was only greater than 40%. In this context, the probability of winning in game A, you knew exactly was 40%. And here, all you knew was the probability of winning was less than 60%, or 60% or less. That's all you knew. So you had uncertainty. You have uncertainty in what the model is when you play game B. You have uncertainty of the game when you play game C. Games A and games D have no model uncertainty. So what you've done is you've really accounted for model uncertainty in your quick evaluation of which games to choose. So that's the context in which I want to develop a framework and then analyze what the consequences of this are. You had a quick question?
If you find 60 black and green, I say expected value of black is 30, expected value of green is 30, and then you do the math and you pick A and C.
Because you just assume 50-50% on here.
You assume that if you have 60 and you consider all possible configurations by maximum.
But then you've put a prior on the probability distribution. So and you could do that, and you would come up with a rational decision. Yes. Yeah.
Yeah. Clearly, we don't like model uncertainty, but I don't think it's inconsistent. The thing is that
it's inconsistent with maximum expected utility.
No, but the thing is that it makes sense. It makes sense to be suspicious and to have a prior that depends on the choice that is offered. So actually, in the first one.
Okay. So sure, you can then say my prior distribution on the probability of black and green depends on the two games that on the choices that are presented to me. You can certainly do this. Yes. Yeah. So the way that I'm going to approach the question of model uncertainty within valuation is rather to use robust control methods. Okay. So this is just a setup to say here's the kinds of problems that people sometimes face and decisions that they make. So there's been a lot of study in this idea of model, or what they call ambiguity aversion or model uncertainty in the literature. One approach is to put priors on parametric. So if I have a model, I can say my model parameter estimate is whatever it is from historical data using maximum likelihood, et cetera, and I can put a prior distribution on those parameters. This would be a parametric assumption on the model, right, and on the prior distribution of this model. Alternatively, you can go ahead and say, you know what, I'm going to consider not just models within that parametric class. I'm willing to consider alternate models that are even outside that parametric class. It will include models that are in the parametric class, but other models which are not. This is related to this notion of robust optimization that's been pushed forward a lot by Hansen. And the terminology that usually goes with this is called nitrogen uncertainty, ambiguity aversion, et cetera. And the idea here is you start with some reference model. So reference measure is like a model. So you've estimated a model. You believe this model to a large extent, hopefully. Otherwise, you wouldn't be using it as a reference. But you're willing to consider the possibility that you're wrong. And you're willing to consider alternate probability models, which represent, it could be within the same parametric family or outside of it. And this is represented by some probability measure Q. And when you're doing a portfolio optimization problem, for example, you would be trying to maximize, instead of just expected utility of wealth, you're going to maximize over all possible trading strategies, but at the same time, take the infimum over all of these other candidate models. But if a candidate model is and at the same time penalize candidate models from reference models, because if a candidate model is too far away from your reference, you have to say, okay, that's bullshit. I don't believe it, right? But if it's very close and you're saying, okay, I'm kind of willing to consider it. In the context of priors, it's like the idea that, well, you have, if I take volatilities as an example, my volatility distribution looks like this, and I expect this is the more likely values, not something that sits in the tail. So it's related to that. A typical penalty here is relative entropy. That's what people will offer, or that's a very common choice for the penalty. It doesn't have to be. You can choose something else. But relative entropy is a particularly useful one. The way that you that you can probe or put your confidence in the model is by putting this parameter here, 1 over epsilon. The idea is that as epsilon goes to 0, anything that is very far away, anything that is even a little bit away from your reference model, the one that you've calibrated to your data, is going to get penalized extremely heavily. So as epsilon goes to 0, it's the analog of saying that I actually really believe in my reference model. My reference model is correct. As epsilon goes to infinity, then this entire term goes away, and the idea is that all other candidate models are just as good as my reference one. I have I believe them all likely. So this would be the idea with epsilon going to infinity would be that you're evaluating the optimal strategy contingent on the worst case scenario coming up. That's one way of interpreting why you have an inf there. Okay, so this is the general idea of what we're going to do, and we're going to apply this in the context of commodity models. Okay, so as we know, all models are wrong, some are useful. Okay, so let's take a look at the type of data that I'm thinking about here is motivated by, say, electricity prices. This is the local marginal price at the PJM grid, which is the Pennsylvania, New Jersey, Maryland grid, and there are a lot of these electricity grids where you transmit electricity from one area to another. But this is just a particular local price. And as you can see, it spikes a lot. There's a lot of spikiness to it. There's spikes that are even negative prices. So you might think, wow, negative prices. Hey, wait, never see that in equity markets and so on. But you do have this in electricity. You would actually be paid to consume the electricity because there's an overproduction of it. Paid to consume it, to receive it. Yeah. So this is a kind of a typical thing you'll see. Oil prices are, of course, not like that, but there are jumps and spikes and so on. And the other thing you'll notice is that there's, the prices kind of fluctuate around some level here. So they're getting pulled back to this level. There's a strong mean reversion component. If you look a little more refined, this is over 1 week here. You can see you get these spikes, and then they tend to come back down within just a few days. But nonetheless, prices are still fluctuating around here. So the 0th order model, our reference model that we're going to choose here, is one that has those features. Those features you can also see in other commodities that are related to energy and even metals and so on. This is going to be, we're going to take 2 forms. We're going to assume that there are 2 main factors to prices. There's a diffusive factor, x, and there's a jump component, y. They're going to be added together. And theta here is just a deterministic function that is a seasonality factor. So if you're thinking of things like electricity, prices can be higher. There can be daily seasonality. It's higher in the morning and afternoon when people come home and turn things on, et cetera. Or if you're thinking about gas, natural gas, it'll be higher in the winter because people heat things and so on. So that's going to be absorbed in this theta parameter. All of the fluctuations, the sort of small fluctuations, are going to be in x, and the big jumps are going to come in y. So x, the diffusive component, it's not just going to be a mean reverting process. We're actually going to take mean reverting, and I know that Chris doesn't like the Heston model here, but we've chosen the Heston model. However, we're using model uncertainty, so we're going to be probing other ones. Okay? So the Heston is the base model here. So we have a mean reverting to 0. Oh, there's a dt missing there. And there's a dt missing there. Oh, gosh. Okay. Call the talk off. It's done.
You are forgiven.
Yeah. So there's mean reverting to 0 there. And this here is the volatility component, which is following a Feller process. And these are the mean reversion levels, the rate, and the vol of vol, as they like to call it. And there's some correlation between these 2 components, the Brownian components for x and for the variance process. While y encodes the jump noise, and this is the part which comes back to 0, this could be very large. The mean reversion for y could be very large, while the mean reversion for x doesn't have to be. One mistake that's often done, I would say, or not often, that used to be often done with commodity models, is people would put this jump component in that equation there for x and not have this y separate. But this would force the mean reversion of the diffusions to be very large in order to pull the jumps back down, and then that means that you have to make the volatility of the diffusion very large to compensate, and it's just bad. So here, you're allowed to have these 2 different factors so that diffusive stuff has its own rate of mean reversion, while jump has its own rate of mean reversion. You really separate the scales, because it's important to separate those scales. Okay, so this is our base model. Now, we've got to talk about the class of alternate models. Now, I mentioned that we're using relative entropy. Now, don't focus on the mathematics. So those of you who are not, interested in the details of it, just think of the intuition that I'm going to use here. What we'd like to look at as alternate models is to first of all, take the Brownian motions and just change their drifts in a potentially stochastic manner. It can be Markov. In particular, we'll restrict it to Markov in the state variables that we have. So that's Markov in x, y, and v. Okay? So you stochastically change the drift by some process alpha. That's going to define one potential probe of alternate models. So if you go here and you imagine just changing the drift of this and the drift of that, suppose I changed it in a way that was proportional to changed the drift of x so that it was proportional to this inverse square root of v. Then all I would do is I'd be adding a drift to x. I'd be adding some sort of constant, if I think of it just as a constant times inverse square root v. Then that would just add a constant drift to x, and I'd be thinking that the diffusive is moving upwards. If I added in square root v times a constant to this Brownian motion, then what I'd effectively do is change the level of mean reversion of v, which means I'd be probing higher volatilities. So this is something that's kind of interesting. I can use measure changes which keep the two probability measures, the reference and the alternate, within they're equivalent to one another because we're using the Radon-Nikodine derivative and just shifting Brownian motions. Yet I'm allowed to change the effective volatility that I see in the model. This is something that you can't do if I did not use a stochastic volatility model. Yeah.
You can if you use a discrete process.
Yeah, sure. If you do things with discrete, you can certainly do that. Yes.
It's a weight.
Absolutely. Fully agree. Fully agree. Yeah. I don't want to do discrete. So with the continuous version, this is a nice way of allowing you to stay within equivalent probability measures and still affect volatility of your diffusive components. Okay, so are we okay with that? Right? We can basically change the drift of x and.
I'd just like to add one more comment to that. Take it very personally because I've done a lot of work with that.
Uh-huh.
Even you can push it to you can discretize first, calculate the entropy,
Mm-hmm.
and then take a limiting distribution.
Yes.
And then the entropy becomes a utility function, and you can sort of control on the volatility. It becomes a control problem.
Okay, cool. I want to talk to you more about that then, after, for sure. Sounds good. Okay, so this is the diffusive candidate class of models, but then we also have the jump component. And again, forget the math. Forget this. This is a particular martingale that allows us to compensate with the random measure, which is driving the jumps of the process there. Here's the real important part of it. So imagine that I had a jump distribution, which was, maybe I can write on the board here. It might be easier. Think of the jump component that shows up here as a very classical example that's used in a lot of places in finance, and in particular as well in commodity models, is to have a double exponential jump. So you have jumps that are positive with some. So if a jump arrives, it arrives at some rate lambda. When it arrives, the distribution is given by an exponential distribution, where x here is the size of that. Maybe I should use little y or little z. Little z is the size of that jump, and then you have a negative component, which does not have such a large mean. As you can see from the data for the electricity, the negative jumps are much smaller. Okay? So imagine that this is my reference model. That's the one that I started with. What's going to happen in my candidate models here is I'm simply going to take this distribution and multiply it by e. The reason I choose the exponential of something is it just happens to make things particularly simple. Multiplied by e to the gtz. This is a random field. So little t represents the stochasticity in time. The z component tells me how I'm going to perturb this probability distribution. So you can think of the time component somehow as making the rate potentially stochastic, and the dependence on z here as potentially perturbing this and, say, maybe emphasizing positive jumps and suppressing negative ones, as an example. Okay? So those are the alternate models that we're allowed to consider. The g function can also be can depend on the Brownian motions that we had before. So it would be allowed, perfectly allowed. Okay, so these are our class of candidate models. Are we all on the same page? Okay, we have the diffusive stuff, changing the drifts potentially of the diffusion component x and the volatility process. We have the jump component that allows us to probe stochastic rate of arrivals and potentially perturb the distribution of jumps. Okay, now, yeah, this is perhaps a bit silly to draw here, but I'll describe it anyway. So if I'm starting with a reference model, and this is my candidate model that's perturbed by alpha, which is the drift adjustments, and g, which is the jump adjustments, I could potentially get there by actually first only changing drifts, then changing jumps, or changing jumps and then changing drifts. There's actually, we can actually do that. And if you look at it like this, you can think of the entropy, relative entropy is broken up into two terms here. This is the term which counts for diffusive changes of candidate models. And this matrix phi inverse represents our model uncertainty. And it has some form like that. Forget about the explicit form. Just think phi here represents our model ambiguity. As it goes to 0, we're model certain. As it goes to, yes, phi goes to 0, we're model certain because it's 1 over phi. As phi goes to infinity, we're model ambiguous. We don't know what model is correct. Similarly, epsilon here, this is effectively the relative entropy for going from a base model, or reference one, to this candidate one where we've, rescaled the compensator of the random measure by this. Okay, so that's the intuition. Explicit forms of it is not so important. I just want to put it there so that you understand the idea. What's important, though, is that this and this are different. This penalty is not exactly relative entropy. It would be relative entropy if I chose this matrix phi to only be 1 over epsilon times the inverse covariance matrix here. Then we get exactly relative entropy. Having this degree of freedom in this matrix and having this parameter not, having these two parameters not directly related to one another allows me to probe ambiguity on the jumps separately from ambiguity on the diffusion component, and it allows me to distinguish ambiguity in volatility from ambiguity in the drift component of x. Okay? It allows you to do that without, and if you did it only with the relative entropy, you have to treat them all the same, and there's only one parameter. So that's a subtle thing for those who know something about model ambiguity. Okay, so forward prices is the next thing I'd like to look at. Now we have the class of, so now we have our reference model, we have the potential class of alternate candidate models, we know how we're going to penalize those alternate models. Now how are we going to do some valuation?
So you're going to, basically you wrote down the change of measure, but now you're going to tell me what you're going to calibrate it or something?
No, I'm going to say, you do the hard work of calibrating, right? You take the data and you calibrate your reference model for me. And now once you've got those parameters, those theta as a function of time, kappa, blah, blah, these parameters here. Now you're giving me that, now I'm going to tell you what to do with it, right? By considering these candidate alternate models. So the first thing that we're going to do is just look at forward prices, because it's really, the intuition that you get from all the forward price calculation translates into what you would do for option valuation. And I'll show you some of the results for forwards, but for options, but we'll go through a little more of the detail in forwards. So if you did the following thing, if I said that my utility is exponential, okay, and I asked for the indifference price using utility. So what does that mean? That means solve a stochastic control problem or portfolio optimization problem where I'm not subject to the risk of the forward contract. I'm only trading in the underlying thing. And then secondarily, solve the problem where I've sold a forward or bought a forward and increased or decreased my wealth, and then optimize. If I find the amount that I have to increase or decrease to make these two value functions the same, that's called your indifference price. Okay? If you did that, you would have something that looks like this. We're not doing that. Okay? We're doing instead a model, a setup where we are risk-neutral agents, but we are ambiguity-averse.
What does it mean to be risk-neutral?
What does it mean to be risk-neutral here? Well, my utility gamma goes to 0. Right? If you divide by gamma, normalize it, then my utility is linear. That's what I mean by risk-neutral here.
So that means
So I'm not changing to a risk-neutral measure in that context. Pricing by expectation.
But you don't know which Q.
But I don't know which Q to use, exactly. So that's what I have here. So for commodities, the nice thing is, of course, that when you, even if I took the classical no arbitrage pricing approach to commodity modeling, if I translate from the real world measure to the risk neutral measure, if I have mean reversion in prices in real world, I still have mean reversion in risk neutral, unlike if that was an equity, for example. I'd have to have the drift as R once I translate to risk neutral world. For commodities, that's no longer true because there are things like stochastic convenience yield and so on. So pricing starting with our reference model, which we can interpret as a risk neutral measure for the agent, and now probe candidate models. So this here is the payoff of the forward contract that pays from T1 to T2. So a forward contract simply pays the spot price from the start of the horizon to the end. That's it, just continuously and averaged. Okay? Forward contracts actually deliver, at least things for like oil, for electricity and so on, you actually deliver over a period. There's a delivery period. It doesn't happen at an instant in time, unlike what you idealize when you teach about forward contracts in this context. So there's an interval over which you deliver, and then there's this penalty that we have, which is our that sort of relative entropy between our candidate, our reference, and our candidate. And we're going to take the infimum over this thing. And there's a plus or minus sign there and a plus or minus sign there, depending if we're a buyer or a seller. You flip things around. So if you're a buyer, all of these are positive signs. If you're a seller, basically remove these plus minus and that plus minus and make that a minus. Okay? It's just flipping the sign. So we're going to focus, I think, mostly on the buyer case here. So I want to figure out, well, what is this value function? What is this value that I'd assign to this forward contract from the buyer-seller perspective? So in this arithmetic model, things are very nice. It turns out, well, okay, in the arithmetic model, so there's a dynamic programming principle that holds here. You can go through and write down the Hamilton-Jacobi-Bellman equation for this thing. Forget about the details. We don't really care. Important thing is H turns out to be a fine in all of the state variables. So it's a function of time plus another function of time times the diffusive factor x plus another function of time times the variance process v plus the function of time times y. Now, anyone who's played with commodity models, arithmetic commodity models, with stochastic volatility and jumps, you might remember that in arithmetic models, this component with variance does not show up. The fact that volatility is stochastic is irrelevant. The volatility process does not show up. Only the state x and y. The actual size of the diffusion, the level that it's at, and whether you currently are in a jump or not. Volatility doesn't show up when you use an arithmetic model. For exponential models, that's not true. Exponential models, the variance does show up. What's curious here is once you consider model ambiguity, variance, volatility does play a role, even in the value in the arithmetic model. So that's kind of an interesting curiosity.
Why do you think that is?
I know why that is. I don't just think, I know why. So the reason is because you're willing to consider alternate models. The drift of your X process turns out to actually depend on the volatility in those alternate candidate models. So the level of X alone is not enough to tell me where X is going to go. So I need to know V. And it's sort of, you can sort of see it here. So alpha star and G star, these are the optimal measures picked out by this agent. So when you solve the HJB equation, you have to do an infimum over the set of jump disturbances and over the set of the drift adjustments. And it's kind of nice that they factor in a way. They're interrelated through the value function, but they factor in terms of their optimization, which is cool. Their optimal points have this form. And you can see the drift adjustment actually is proportional to square root v times some function of time and times the ambiguity matrix, et cetera. The jump adjustment turns out to be also linear. Well, it's linear in the uncertainty parameter or ambiguity parameter, and it's linear in the z. So this thing here just becomes like an exponential tilting. It's almost like an Escher transformation for those of you who know about Escher, but it depends on it, but it's a function of time. Deterministic function of time, the amount that you distort. That's for the buyer. For the seller, it looks the same except the signs are flipped. So there's kind of interesting results. Okay, forget what that is. Let's skip that. Let's skip that. Let's skip that. And skip that. And show show the, what I want you to see is I want you to see the, this is what I want you to see, yes. In the interest of time, there's lots of, I have like quite a few slides here. This has not been cut down for the 45 minutes version of things, but I'm presenting the cut down version. So what I'm showing you here is a simulated path after, say, calibrating some reference model. The black line there is a simulated spot price. The red and blue that you see there, there's a tiny gap. That red and blue is the buyer and the seller's ambiguity adjusted forward price. Okay? Now, if you look at, so there's a couple of things you can note just from this top panel, first of all. One, there's a jump that happens in the spot price here, but the forwards do not, don't jump at all. So what's the intuition there? Why did that happen? Well, if you remember from the plot of the data, when you had jumps in spot, they tend to go away fairly quickly. The maturity of this forward was at the end of the period here. So in expectation, this jump is going to go away, so the forward does not respond to that jump. However, there's a jump here that happens, and the forward does respond to that because it's going to mature fairly soon. So it will be exposed to that jump component. Okay? So that's a simple, nice little intuition there. The other thing is, if you look at the spread between the seller price and the buyer price, that's the panel down here now. What I'm showing you is a few different things. So in this panel, I'm showing you what happens when you vary the ambiguity to the jump component only. So the ambiguity to the diffusion is fixed at something, and I slowly increase the ambiguity to the jump component. So you get this blue line for the spread. That's the difference between the bid, the bid and the ask, and you get this blue line. As I increase ambiguity, I push that spread up. But what's interesting is that that spread is only biased upwards initially. Toward, as you move further along, the ambiguity doesn't affect the spread terribly much. That's kind of an interesting feature. The other thing is there's a dotted line that's showing up here. Do you see the dotted lines? They're below every one of those. There's the red kind of stochastic curve, a green one, and a blue one. If you look right below it, there's a dotted line. The dotted line shows what the spread would be if you did not use stochastic volatility. If volatility was deterministic, or I think it was actually set to be constant for the comparison. So one thing you notice is that the premium due to stochastic volatility in the spread is small initially, but becomes larger later on. So you can interpret the difference between any one of the colored curves and the dotted line as a premium due to stochastic volatility in this setup. And that's another interesting thing to see, that it's mostly affected toward the later part of the process rather than earlier on. The second panel that's here, this right one, shows what happens when I fix jump ambiguity, but I vary the ambiguity to the diffusions. And it's qualitatively quite different. It pushes the spread up throughout the entire time horizon rather than only biasing the initial spread. It still biases this side more than this side, but it pushes it up everywhere else. And once again, you can see the premium due to stochastic volatility is the difference between any one of these colored curves and the dotted line. And the other thing you can observe is that the premium due to stochastic volatility, as you increase ambiguity in the diffusion components, are higher, because that's where the volatility resides. It's in the diffusive components. Now, of course, I could repeat this entire thing and put a jump component in volatility and have model ambiguity on that thing, but this is already giving enough interesting qualitative features, and that's what we wanted to see. Okay, how much time? I think I've got like 10 minutes or less. That's good. So, a couple of points. Mean reversion, when you look at this alternate, this setup, and you find the optimal measure, the mean reversion of x is actually modified as per this key result here. Okay, the level of x gets scaled up by square root v. So x actually mean reverts to a stochastic level. The other interesting output is the mean reversion rate and level of the variance process is also modified. What's interesting is that the buyer actually thinks that volatility effectively pushes the volatility level down and the rate of mean reversion up. So it actually concentrates volatility. The seller does the opposite. The seller pushes the level of mean reversion of variance up and reduces the rate of mean reversion so that there's more stochasticity in volatility. And the jump and arrival rates are altered. But what's curious is that there's no cross effect between the diffusive and jump components here. Somehow they've factored out entirely, even though they affect one another indirectly through those affine functions that show up in the price, but they somehow, there's no crossing effects. And that's what we're going to see when we look at the exponential case. So I'm not going to go through the details of the exponential case. I'm just going to skip straight off to the simulation in the exponential case. And here's the analog of the 3 plots we saw before, where we now take the exponential of theta plus x plus y, and we've recalibrated it so that they produce qualitatively the same type of sample paths. So here you see there's a spike in the forward price, but now there actually was a little bit of a jump in the forward here. Still, most of the jump happens at this end. What's interesting, and we did not see in the previous case when we had an arithmetic model, is that the jump in the forward price actually induced a jump in the spread. Before, the jump in the jump process, the jump component in our spot price had little effect on the forward, and it had no effect on spread. Here, we're actually seeing an interaction. So this is one of the kind of interactions that I'm talking about. And again, this is just showing you what happens as you vary the increase the rate of, the model ambiguity. You move upwards here. And as you increase model ambiguity in jumps, as you increase model ambiguity in diffusion. And you have similar idea that most of the adjustments happen earlier on, and this becomes tighter relative to what happens for the diffusion case. Okay. Right. Okay, so the last thing I want to show you is another just example of the results, is what happens when you do an option price in this setup. So not the forward contract, but imagine I have an option on the forward. So you use this methodology to get an ambiguity-adjusted forward price, and that ambiguity-adjusted forward price feeds into an option valuation, which you then project backwards. Okay, so it's more or less the backwards programming idea, except the payoff is that of an option and not that of a forward. So first of all, let's look at the left panel. What we looked at here is a bull spread. So this is the thing that is 0. At 15, it starts going up linearly at 1, and then flattens out at 25. So it's a long call at 15, short call at 25. That's what we mean by a bull spread. As a function of x and y, remember the price is made up of both x and y. So the sum of these two things somehow give us the spot price when you exponentiate. What you find is that, well, if x and y are both negative, then the option is going to be out of the money. So it has very little value. When x and y are both positive, then the option has a lot of value. It's in the money. So that's what you're seeing in this panel. Little value moving into a lot of value. That's just moving out of the money into the money. The question or the result that I think is interesting is you ask, what about the spread between buyer and seller? How does that vary as a function of where the spot price is? This is the result you find. So wherever there's a cyan color, the optimal measure is close to the reference model. It turns out that, because remember, this optimal measure is some sort of stochastic thing, right? And if you look at the drift adjustments and the jump adjustments, when you're in this region or this region, you actually behave as if the model is the same as a reference model. So why is that? Because if you're in this region or in this region, that's the part where the payoff, it's out of the money or in the money. No matter what my model is, I'm going to get 0 or I'm going to get 10. So model uncertainty does not affect my valuation. However, when you're in the part in between where there's, the premium still increasing, that's where option valuation is most sensitive. And you see deviations. You see that the spread increases and it's maximized right toward x and y are 0. Oh, geez. I hope what does that correspond to again?
Midpoint.
It should be midpoint between the 15 and 25s. It should be. But I don't remember. Huh?
That is very counterintuitive.
That's counterintuitive.
Yes.
Why? Because they're. Whoop. Okay, that tells me 40 minutes is up.
If an option trader thinks about it,
Yeah.
there is a point in the call spread that there's no convexity. It's the inflection point,
Sure.
which is at
Okay.
some point, there's no vega. In fact, there's something called the midpoint rule.
Sure.
It says that the call spread should be priced exactly at the middle between half point between the two strikes. Right? So if you have an ambiguity there, it can only come from the ambiguity forward.
Mm-hmm.
But if you fix the
Yes,
forward-
yes, yeah, but this is not fixing the forward.
Yeah, but if we don't fix the forward, option pricing doesn't make a lot of sense,
But it's
right?
very sensitive
Yeah.
to skew, actually. If you have a different skew, then the price.
Yeah, and there's a jump model in here, right? You're looking at ambiguity and jumps.
Okay, skew, yes, but
Yeah.
I mean, we all know that the call spread at the midpoint, I mean, if I don't know that, I'm willing to, check in some facility. Yeah, the midpoint is the midpoint, unless you have hard to borrow, yes, unless you have a huge drift because of some special thing.
So remember, in this context, you're considering.
We don't mix the two things when we test something.
Sure.
The forward and then the
Huh? But yeah, so this setup is you're considering the alternate models where the skew could be potentially different, and this is where it affects you the most.
It's
Okay,
not skewed,
so
he has the wrong forward. Don't mix skew with forward.
Yeah, maybe the delta
the forward is
in the middle and more sensitive to the forward.
Yeah, but everybody has, if you don't put the forward, you shouldn't be in the business of pricing call spreads. You should just price whatever.
so the other thing to remember, Marco, is that these are options on things that themselves are not actively traded, right? So this is a spot model. If I knew the exact model for everything, then I think what you're saying is correct.
I totally understand that.
Yeah.
But that's a forward effect. It's not a ball effect. That's what I'm saying. The red is a ball effect. The white is a forward effect.
Could be, could be,
It's also true on the other graph.
could be. Let me see if I have. So
I mean, that's what you do when you stare at this for 20 years.
yeah.
Very fast. Otherwise,
So, okay, the thing is I don't actually have the absolute sign. Do I have the absolute sign here? Buyer, alpha, star. No, this doesn't tell me. I don't have the vol. Oh, no, yeah, I don't have the vol separately here. So I can't tell you off the bat.
I'm telling you,
Yeah.
the forward is the forward.
Yeah,
Respect the forward.
respect the forward. Okay, so let me wrap it up and then we can get more into this one? Option price bid ask spread?
Another one before?
This one?
No, same kind of graph.
This was the one that we've been settled on.
But the other one,
This one, where this is the buyer's optimal drift and the seller's optimal drift.
was actually totally the scale and the color range.
Yeah.
It was corresponding just to a constant value. It's another one that we just went through. Yeah, here.
This one.
Yeah, for instance, you
This is the mean jump size.
yeah. But here it seems to be just actually flat when you look at the value on the color code on the right-hand side.
When you look here, in terms of the y direction,
No, I mean, just the values.
the numerical values. Yes. This is for the jump correction. This is for the junction. This is for what it is that biases the jump distribution. And yes, it's more or less constant in this thing. However, the coloration, yes, it's maybe perhaps deceiving in that sense, but the absolute value of the absolute sign of it or size of it is given by this. The cyan, when I say close to the reference model, the mean of the reference model must have been whatever number that you see that should be there is what the reference model's mean was. So as you move away, you get hotter and hotter. Yeah. But yes, in terms of absolute size, you're right. It's minimal with respect to jump. The diffusive component is the largest biasing feature that shows up here, that shows up in the price and the bid-ask spread. Okay, so let me just give the last slide to conclude. Okay, so we've done this thing where we look at how does model uncertainty affect your valuation in this approach where you have diffusive with stochastic volatility and jumps and some of the interesting consequences of it. What are we doing with this now? We're actually looking at some algorithmic trading problems where you have interconnectors of electricity grids and how you should trade between these two venues in order to take advantage of misprices while still accounting for model ambiguity, as well as we were interested in looking at model ambiguity on tree models. This is related somewhat to the stuff that Ryan has done in the past on algorithmic trading and model uncertainty for market-making problems, but quite different context. Okay, so thank you for your attention.
Thank you very much, Sebastian.